OpenMP is an API that supports multi-platform shared memory multiprocessing programming in C, C++, and Fortran, on most processor architectures and operating systems, including Solaris, AIX, HPUX, Linux, Mac OS X, and Windows platforms. It consists of a set of compiler directives, library routines, and environment variables that influence runtime behavior. OpenMP is managed by the non-profit technology consortium OpenMP Architecture Review Board, jointly defined by a group of major computer hardware and software vendors, including AMD, IBM, Intel, Cray, HP, Fujitsu, Nvidia, NEC, Red Hat, Texas Instruments, Oracle Corporation, and more. OpenMP uses a portable, scalable model that gives programmers a simple and flexible interface for developing parallel applications for platforms ranging from the standard desktop computer to the supercomputer. An application built with the hybrid model of parallel programming can run on a computer cluster using both OpenMP and message passing interface, or more transparently through the use of OpenMP extensions for non-shared memory systems. Introduction. OpenMP is an implementation of multi-threading, a method of parallelizing whereby a master thread forks a specified number of slave threads and the system divides a task among them. The threads then run concurrently, with the runtime environment allocating threads to different processors. The section of code that is meant to run in parallel is marked accordingly, with a preprocessor directive that will cause the threads to form before the section is executed. Each thread has an id attached to it which can be obtained using a function. The thread id is an integer, and the master thread has an id of 0. After the execution of the parallelized code, the threads join back into the master thread, which continues onward to the end of the program. By default, each thread executes the parallelized section of code independently. Work-sharing constructs can be used to divide a task among the threads so that each thread executes its allocated part of the code. Both task parallelism and data parallelism can be achieved using OpenMP in this way. The runtime environment allocates threads to processors depending on usage, machine load and other factors. The runtime environment can assign the number of threads based on environment variables, or the code can do so using functions. The OpenMP functions are included in a header file labeled OmpH in C++. History. The OpenMP Architecture Review Board published its first API specifications, OpenMP for Fortran 1.0, in October 1997. October the following year they released the C++ standard. 2000 saw version 2.0 of the Fortran specifications with version 2.0 of the C++ specifications being released in 2002. Version 2.5 is a combined Fortran specification that was released in 2005. Version 3.0 was released in May 2008. Included in the new features in 3.0 is the concept of tasks and the task construct. Version 3.1 of the OpenMP specification was released July 9, 2011. Version 4.0 of the specification was released in July 2013. It adds or improves the following features: support for accelerators, atomics, error handling, thread affinity, tasking extensions, user-defined reduction, SIMD support, Fortran 2003 support. The core elements. The core elements of OpenMP are the constructs for thread creation, workload distribution, data environment management, thread synchronization, user-level runtime routines and environment variables. In C++, OpenMP uses pragmas. The OpenMP-specific pragmas are listed below. Thread creation. The pragma parallel is used to fork additional threads to carry out the work enclosed in the construct in parallel. The original thread will be denoted as master thread with thread ID 0. Example: display hello, world. Using multiple threads. Use flag for OpenMP to compile using GCC. Output on a computer with 2 cores, and thus 2 threads. However, the output may also be garbled because of the race condition caused from the 2 threads sharing the standard output. Work-sharing constructs, used to specify how to assign independent work to one or all of the threads. OMP or OMP2, used to split up loop iterations among the threads, also called loop constructs. Sections, assigning consecutive but independent code blocks to different threads. Single, specifying a code block that is executed by only one thread. A barrier is implied in the end. Master, similar to single, but the code block will be executed by the master thread only and no barrier implied in the end. Example, initialize the value of a large array in parallel, using each thread to do part of the work. OpenMP clauses. Since OpenMP is a shared memory programming model, most variables in OpenMP code are visible to all threads by default. But sometimes private variables are necessary to avoid race conditions and there is a need to pass values between the sequential part and the parallel region, so data environment management is introduced as data sharing attribute clauses by appending them to the OpenMP directive. The different types of clauses are: data sharing attribute clauses, shared, the data within a parallel region is shared, which means visible and accessible by all threads simultaneously. By default, all variables in the work-sharing region are shared except the loop iteration counter. Private, the data within a parallel region is private to each thread, which means each thread will have a local copy and use it as a temporary variable. A private variable is not initialized and the value is not maintained for use outside the parallel region. By default, the loop iteration counters in the OpenMP loop constructs are private. Default allows the programmer to state that the default data scoping within a parallel region will be either shared, or none for C++, or shared, first private, or none for Fortran. The none option forces the programmer to declare each variable in the parallel region using the data sharing attribute clauses, first like private except initialized to original value. Last like private except original value is updated after construct. Reduction, a safe way of joining work from all threads after construct. Synchronization clauses, critical, the enclosed code block will be executed by only one thread at a time, and not simultaneously executed by multiple threads. It is often used to protect shared data from race conditions. Atomic, the memory update in the next instruction will be performed atomically. It does not make the entire statement atomic. Only the memory update is atomic. A compiler might use special hardware instructions for better performance than when using critical, ordered. The structured block is executed in the order in which iterations would be executed in a sequential loop. Barrier, each thread waits until all of the other threads of a team have reached this point. A work-sharing construct has an implicit barrier synchronization at the end. Wait specifies that threads completing assigned work can proceed without waiting for all threads in the team to finish. In the absence of this clause, threads encounter a barrier synchronization at the end of the work-sharing construct. Scheduling clauses, schedule, type, chunk. This is useful if the work-sharing construct is a do loop or for loop. The iteration, s, in the work-sharing construct are assigned to threads according to the scheduling method defined by this clause. The three types of scheduling are: static here, all the threads are allocated iterations before they execute the loop iterations. The iterations are divided among threads equally by default. However, specifying an integer for the parameter chunk will allocate chunk number of contiguous iterations to a particular thread. Dynamic, here, some of the iterations are allocated to a smaller number of threads. Once a particular thread finishes its allocated iteration, it returns to get another one from the iterations that are left. The parameter chunk defines the number of contiguous iterations that are allocated to a thread at a time. Guided, a large chunk of contiguous iterations are allocated to each thread dynamically. The chunk size decreases exponentially with each successive allocation to a minimum size specified in the parameter chunk. If control, if, this will cause the threads to parallelize the task only if a condition is met. Otherwise the code block executes serially. Initialization, first the data is private to each thread, but initialized using the value of the variable using the same name from the master thread. Last the data is private to each thread. the value of this private data will be copied to a global variable using the same name outside the parallel region if current iteration is the last iteration in the parallelized loop. A variable can be both first private and last private. Thread private, the data is a global data, but it is private in each parallel region during the runtime. The difference between thread private and private is the global scope associated with thread private and the preserved value across parallel regions. Data copying, similar to first private for private variables, thread private variables are not initialized, unless using copy-in to pass the value from the corresponding global variables. No copy-out is needed because the value of a thread private variable is maintained throughout the execution of the whole program. Copy private, used with single to support the copying of data values from private objects on one thread to the corresponding objects on other threads in the team. Reduction, operator intrinsic list. The variable has a local copy in each thread, but the values of the local copies will be summarized into a global shared variable. This is very useful if a particular operation on a data type that runs iteratively so that its value at a particular iteration depends on its value at a prior iteration. Basically, the steps that lead up to the operational increment are parallelized, but the threads gather up and wait before updating the data type, then increments the data type in order so as to avoid racing condition. This would be required in parallelizing numerical integration of functions and differential equations, as a common example. Others, flush, the value of this variable is restored from the register to the memory for using this value outside of a parallel part, master, executed only by the master thread. No implicit barrier. Other team members not required to reach. User-level runtime routines, used to modify check the number of threads, detect if the execution context is in a parallel region, how many processes in current system, set unset locks, timing functions, etc. Environment variables, a method to alter the execution features of OpenMP applications. Used to control loop iteration scheduling, default number of threads, etc. For example, OMP threads is used to specify number of threads for an application. Sample programs. In this section, some sample programs are provided to illustrate the concepts explained above. Hello World, a basic program that exercises the parallel, private and barrier directives, and the functions ompGetThreadNum and ompGetNum threads. C. This C program can be compiled using GCC 4.4 with the flag FOPEMP. C++. This C++ program can be compiled using GCC, G++ wall FOPEMP test CPP. Note, the IOStreams library is not thread safe. Therefore, for instance, count calls must be executed in critical areas or by only one thread. Fortran 77, here is a Fortran 77 version. Fortran 90 freeform, here is a Fortran 90 freeform version. Clauses in work-sharing constructs. The application of some OpenMP clauses are illustrated in the simple examples in this section. The piece of code below updates the elements of an array B by performing a simple operation on the elements of an array A. The parallelization is done by the OpenMP directive pragmaomp. The scheduling of tasks is dynamic. Notice how the iteration counters J and K have to be made private, whereas the primary iteration counter I is private by default. The task of running through I is divided among multiple threads, and each thread creates its own versions of J and K in its execution stack, thus doing the full task allocated to it and updating the allocated part of the array B at the same time as the other threads. The next piece of code is a common usage of the reduction clause to calculate reduced sums. Here, we add up all the elements of an array with an I-dependent weight using a for loop, which we parallelize using OpenMP directives and reduction clause. The scheduling is kept static. An equivalent, less elegant, implementation of the above code is to create a local sum variable for each thread, and make a protected update of the global variable sum at the end of the process, through the directive critical. Note that this protection is critical, as explained elsewhere. Implementations. OpenMP had been implemented in many commercial compilers. For instance, Visual C++ 2005, 2008, 2010, 2012 and 2013 support it, as well as Intel Parallel Studio for various processors. Oracle Solaris Studio compilers and tools support the latest OpenMP specifications with productivity enhancements for Solaris OS and Linux platforms. The Fortran, C and C++ compilers from the Portland Group also support OpenMP 2.5. GCC has also supported OpenMP since version 4.2. Compilers with an implementation of OpenMP 3.0, GCC 4.3.1, Mercurium compiler, Intel Fortran and C++ versions 11.0 and 11.1 compilers, Intel C++ and Fortran Composer XE 2011 and Intel Parallel Studio. IBM XLC C++ compiler, Sun Studio 12 Update 1 has a full implementation of OpenMP 3.0, several compilers support OpenMP 3.1, GCC 4.7, Intel Fortran and C++ compilers 12.1, compilers supporting OpenMP 4.0, GCC 4.9.0 for C++, GCC 4.9.1 for Fortran, Intel Fortran and C++ compilers 15.0, auto-parallelizing compilers that generate source code annotated with OpenMP directives, IPATOMP, Parallelware, Pluto, ROSE, S2P by KPIT. Cummins Infosystems Limited. Pros and cons. Pros: portable multi-threading code. Simple, need not deal with message passing as MPI does. Data layout and decomposition is handled automatically by directives. Scalability comparable to MPI on shared memory systems. Incremental parallelism, can work on one part of the program at one time, no dramatic change to code is needed. Unified code for both serial and parallel applications. OpenMP constructs are treated as comments when sequential compilers are used. Original code statements need not, in general, be modified when parallelized with OpenMP. This reduces the chance of inadvertently introducing bugs. Both coarse-grained and fine-grained parallelism are possible. In irregular multiphysics applications which do not adhere solely to the SPMD mode of computation, as encountered in tightly coupled fluid particulate systems, the flexibility of OpenMP can have a big performance advantage over MPI. Can be used on various accelerators such as GPGPU. Cons: risk of introducing difficult-to-debug synchronization bugs and race conditions. Currently only runs efficiently in shared memory multiprocessor platforms. Requires a compiler that supports OpenMP. Scalability is limited by memory architecture. No support for compare and swap. Reliable error handling is missing. Lacks fine-grained mechanisms to control thread processor mapping. High chance of accidentally writing false sharing code. Multi-threaded executables often incur longer startup times than single-threaded applications, therefore if the running time of the program is short enough there may be no advantage to making it multi-threaded. Performance expectations: one might expect to get an n-times speed-up when running a program parallelized using OpenMP on a in-processor platform. However, this seldom occurs for these reasons. When a dependency exists, a process must wait until the data it depends on is computed. When multiple processes share a non-parallel proof resource, their requests are executed sequentially. Therefore each thread must wait until the other thread releases the resource. A large part of the program may not be parallelized by OpenMP, which means that the theoretical upper limit of speedup is limited according to Amdahl's law. N processes in a symmetric multiprocessing may have n times the computation power, but the memory bandwidth usually does not scale up n times. Quite often, the original memory path is shared by multiple processors and performance degradation may be observed when they compete for the shared memory bandwidth. Many other common problems affecting the final speedup in parallel computing also apply to OpenMP, like load balancing and synchronization overhead. Thread affinity: some vendors recommend setting the processor affinity on OpenMP threads to associate them with particular processor cores. This minimizes thread migration and context switching cost among cores. It also improves the data locality and reduces the cache coherency traffic among the cores. Benchmarks. There are some public domain OpenMP benchmarks for users to try. NAS Parallel Benchmark, OpenMP Validation Suite, OpenMP Source Code Repository, EPCC OpenMP Micro Benchmarks, Learning Resources Online, tutorial on llnl.gov, reference tutorial page on nersc.gov, tutorial NCI Tutor, see also. References. Further reading. External links. Official website includes the latest OpenMP specifications, links to resources, and a lively set of forums where questions about OpenMP can be asked and are answered by the experts and implementers. GOMP is GCC's OpenMP implementation, part of GCC, IBM Octopillar with OpenMP support. Blaise Barney, Lawrence Livermore National Laboratory site on OpenMP, OMCA, an application in Readlib project for the interactive symbolic model checker of C++ programs with OpenMP directives, combining OpenMP and MPI, mixing MPI and OpenMP.